ask your question by unmuting. Welcome to Fission Tech Talk. It is October 18th, 2023, and we're joined by John, based in Toronto, who's going to walk us through Source Network. Take it away, John.
Beautiful. Thank you, Boris. I'm John. I'm going to be going through some stuff, some casual things we're doing here and there in and around the ideas of decentralization and privacy and security and self-sovereignty. And, someone shouted out democratization of data. And that's all very much our jam here at Source. And so, this is casually titled Sorcery with Decentralized Databases. That's primarily because the idea of putting that on a title seems a little absurd. I'm trying to put in exactly what we do. So we're just going to go with sorcery with decentralized databases for now. I'm John Simmons. I'm the CTO here at Source Inc. We are working on a public and permissionless network called Source Network, of which there is kind of four primarily pieces of tech that make that happen. I'll be giving a brief overview on kind of like the Source Network stack as a whole, but really we'll be diving into two specific core components as it relates to our decentralized database and our authorization engine called Zanzi. And so for context, because we always like having some context when we like to understand problems and solutions, there's kind of been this pretty significant stagnation that's pretty prevalent throughout really like the computing world and the online interactivity world and all that fun stuff. I feel like we made a lot of good progress. We went from the papyrus and etching on stones and moved to proper paper and the printing press, and moved on to digital filings and PCs and all that fun stuff into the cloud. And then apparently we're at this like beautiful quote unquote decentralized utopian future, or at least we're supposed to be right now. But it's unsurprisingly that like kind of the way we've managed data and the way that we've kind of developed apps to manage data has really been foundationally the same really for since the quintessential IBM digital office from the 60s and 70s. And so, really fundamentally what that does to our data is it creates these like issues of fragmentation. Everything is by design siloed, right? And we like to tout that out as a good thing. You want your walled gardens, you want to scoop up all your users as fast as possible and put a moat around them. And it seems great for the land of VCs because they get to 10x their money and walk off into the sun. But for the actual utility of users, having all your data locked away behind this moat that is by definition proprietary, it is gated by the whims and wills of sorry, I was getting some feedback there. The whims and wills of whatever the application decides or not decides, and the rising falling of the tides of permission policies and terms of use, and it's foundationally just it's a fundamentally broken problem. And really, it's ultimately vulnerable, right? Having all your data just kind of this one place, hoping that we're not going to get hacked or not going to have some sort of data breach. It's kind of this absurdity, right? It's not a matter of like if we get breached or if there's a vulnerability. It's simply a matter of when. And so, trying to design systems to gracefully fail at the time that we actually needed to is pretty paramount. And so, for us here at Source, we kind of have this pretty broad notion, and I'll very much be preaching to the choir with this particular group, but foundationally comes down to these kind of like three core tenets around what kind of like data management fundamentally needs to be, which is rooted in the ideas of decentralization, of which decentralization itself is a pretty loaded word. As you saw at the very beginning of my talk, we use it pretty broadly to mean a lot of different things. But for us, it comes down to a couple core key tenets, and the first of which is like interoperability. We want to kind of break down those silos and those walled gardens and those moats to be able to have the ability for users to dictate, my data's over here, why can't it be over there? My data's in this application, why can't it work with that application? And so the idea of interoperability around open data models is really really important to be able to transfer data between users, devices, use cases, all that fun stuff. And to do that, what we really need to do is not so much have the application and foundationally like the database, the traditional monolithic database, the monstrous and infamous database be the center of the equation. Really, we need to have users kind of be in the center of the equation, and we end up in this domain of like controllability, or what it means to have true ownership and authority and sovereignty over the information and the data that we generate on the internet. And then lastly, unsurprisingly, we just need things to be genuinely more secure. And we need to be in those situations where when there are, security vulnerabilities, when there are data breaches, it is localized and it fails very gracefully. So pretty broad kind of tenets, but this is roughly the driving mechanisms and goals we have here at Source. As I mentioned, the Source stack is kind of comprised of foundationally really 4 key pieces of technology that we've been working on. The main kind of pillar of those technologies is our database, DefraDB, which stands for the Decentralized Infrastructure Database. It's kind of a play on the whole like DeFi world of decentralized finance. I had to go with decentralized infrastructure. Technically, I assume you should pronounce it as Defra if we're playing with the DeFi game, but Defra sounds dumb, so we didn't do it that. And so Defra is kind of the core mechanic. It allows us to do a lot of the things that we really foundationally need to do, of which we then kind of have these series, the accoutrement, the tangential mechanics that all comprise the Source stack. And we'll kind of go through each in very light detail, and then we'll dive into the 2 kind of specific things for the rest of the talk. In general, Defra has kind of a series of functionalities and design points that make it really unique that we'll spend a decent chunk of today's talk talking about. So I won't go through too much here, but in general, we kind of have these like high level points about the deployability, this universal deployability, having the data and the database kind of reside as close to or at the same point together. It's all based around peer-to-peer data mechanics. It's foundationally a NoSQL style document database, has some cool cryptographic state proofs that are being worked on, and it's all wrapped up using CRTTs, which we'll dive all into. But next to that, we have Source Hub, which is an application-specific blockchain. And I've been around the blockchain space since like 2011, stealing electricity from my dorm rooms to run some like crappy miners made out of horrible gaming gear from like 5 years ago, or 5 years prior to the time. And in general, I feel like blockchains suck for like the vast majority of things that we make blockchain suck or do. But there is a very small sliver of things that they are objectively wonderful at. And if you can kind of like hone in on what those elements are, and really kind of minimize reduce the bloat. Really, the problem is around bloat of the utilities and functions and features we try to stuff into blockchains. We try to have them just this like universal magical computer that can do everything. But really, more often than not, we don't actually refer to our Source Hub project as an application-specific blockchain, although it is. We really just more refer to it as our trust protocol. And it's really there just to kind of augment the trust in all these decentralized peer-to-peer databases that are like humming and hawing over the internet. The Source Hub kind of provides that lubricant to facilitate and just more trusted interactions between everyone. And there's a bunch of functionalities and features baked into that, of which the main one that we'll be talking about today in contact or in addition to the database is the permission policy engine, and we'll get into all the fun stuff there. Additional to that, we have Orbis, which is a decentralized on-chain secrets management engine. It's a non-custodial, custodial secrets management engine. And I can spend a whole hour just talking about the beauty of how Orbis works. And it is kind of like somewhat integrated into how authorization works and identities and key pairs and all the fun stuff. But I'll refrain from going into that too much. And if anyone wants to, feel free to hit us up and I'll happily talk your ear off until you tell me to shut up.
When John and I were talking, what I really realize here is the challenge for many of us especially those who started some time ago, was that there weren't any off-the-shelf things. So we had to kind of like we tried to build the thing, but we actually have to go one layer down to build the protocol that supports the auth thing that we're actually get to. So it's amazing to here's someone else who's gone down this path where I know that this decentralized secrets management is something that has started coming up as we look at IPVM and decentralized compute.
Absolutely.
Right. So excited to hear more. And yeah, I think that's a whole other session
A whole
that
other
we should do at some point.
Absolutely. Awesome. And then moving on, to make the actual functions of interoperability and shared data and open data models possible, we've been working on this incredibly powerful and interesting project called Lens VM, which is based around the ideas of Cambria out of Ink and Switch, around the ideas of bidirectional data transformations. And so it's all baked around WebAssembly and allows us to kind of build these adapters, for lack of a better word, these lenses into data so that we can manage the migrations and changing and evolution of schemas over time in a kind of like provable and decentralized and peer-to-peer compliant way. But, again, whole talk of which I've given previously and happy to give again, but it's a complicated subject. But as I mentioned, we'll kind of be talking about these two core primitives, our database and our authorization layer, mostly because, a lot of what we do is baked around the database. And, with this being the audience that it is, we wanted to highlight some of the ways that we do authorization, do authentication, and how we've been exploring UCAN specifically to kind of help us augment our whole vision of decentralized data management. So first, we'll dive into the land of Defra. And hopefully the light background's not completely blinding everyone. So thank you for bearing with me on that one. So we're going to take a brief little history of the, I don't know, where we end up today and how we build applications. And so in the beginning, there was Microsoft. And I'm relying really heavily on this logo here. It really encompasses the introduction of personal computers, where we have our IBMs and our Commodores and moving on to DOS, and so really this idea that we had applications once upon a time. They were native to our computer, and that technically gave us a lot of power. To do things that we actually owning our data, because the data never left our computer. Our word editors, our computer, our photo editors, all these things, they reside directly in our devices. And so that gave us a lot of agency, just because there was no other way to lose that. And then, there was this beautiful revelation of, how much we could actually do on the internet and the dynamic powers that we could get by wiring up PHP and CGI and connecting into our beautiful MySQL databases to power everything. And we actually started to be able to store and do dynamic things and create beautiful, complicated applications. And so it was definitely a bit of a whirlwind. It allowed us to do a lot of good things. It was also most certainly a foot gun situation where we definitely allowed us to do potentially too many things. And with that, we kind of didn't really think about the ramifications of just doing everything online. And instead of taking a moment to really think about what this meant for the internet and how we could kind of combine these two domains of, this original OG local first domains with the interactivity and online of databases and application stacks. And instead we just went full tilt straight to SaaS, without any consideration or concern for what that would actually mean. And it was at this point where the walled gardens and the moats and the silos really got entrenched, and forever for reasons beyond this talk, that was just kind of became the dominant way to build applications, without considering how data and how users and how agency and consent kind of has been dropping off since the earlier days. And then, basically since then, we've just been making some arbitrarily and incremental changes to the architecture without any substantive differences. Going from the monoliths to the microservices and the invention of Kubernetes. And, apparently we're in this beautiful golden age utopia of building out applications on the internet. But we haven't really thought much about what it means to have users in that process, and users that care about privacy, and users that care about consent and agency. And then came along kind of this like Web3 thing, and it was supposed to be like, it'll magically solve everything because we have blockchains and blockchains are great. Then you kind of realize, like, I don't know, are they? And like, is Web3 even like a quote unquote decentralized? Is it purveying and putting forward the ideas that we actually want it to put forward in a way that's like done and decentralized and secure and safe and interoperable and all the good things that we want? Like, is Web3 the thing? And it turns out that no. There is like an overwhelming and concerning amount of centralization, very prolific throughout the entire domain of Web3. And we put a lot of lip service towards the idea of decentralization, and we have this whole marketing gimmicks of like decentralization washing and like so on and so forth. But fundamentally, there are still some pretty core problems to the idea of Web3, and like even the fact that we're trying to like call this whole Web3 thing is kind of absurd. It's really just like another step, not even like a notable step, I would say, in the grand scheme of the evolution of the internet. And I don't think we need to kind of put ourselves up on this high horse and be like, well, we're Web3, and that, but back there is Web2, and Web2 is bad and Web3 is good, because we still really haven't got our shit together. So to take another quick tangential story time, when he went out to start Source, we were actually working on a slightly different project, and at the time, we realized that there was a lot of this kind of like centralization to the system that we were building, this like beautiful magical interoperability play that was just going to be the ultimate plumbing to connect all things to all things. And we're like, well, if we're going to do this, we probably should make it decentralized. We looked around the space, we're like, well, there isn't really too much, but like, hey, there's like this IPFS thing. And so IPFS, we're like, all right, great. That's going to give us like some decentralization, and it's going to give allow us the ability to actually build out applications in a way that we expect to build applications, the way over the last 30 years we've come to kind of understand how to build applications. Going back to the LAMP stack reference, LAMP is actually a really interesting one because it really did cement this idea of how application stacks are going to build out, and we really haven't gone or strayed too far off that path. But we looked at it, we're like, IPFS, cool, that's like a thing. It's a file system, right? It's a file system, right? It's right there in the word, interplanetary file system. Anyways, IPFS has a bit of an identity crisis, and foundationally it is like really powerful. And obviously, again, preaching the choir, Protocol Labs is here. We use IPFS extensively. I'd say 90% of the people on this call use IPFS in one way or another. So what we've actually decided to do is realize that like IPFS being IPFS things, we're actually going to take a step back and build out a brand new database from scratch. And this is starting now 5 years ago, to build out a database based around these core principles of IPLD and libp2p. And that's basically what we did. 5 years later, give or take a couple of moons. It is open source. It's live. Technically it's source available right now. It's under a BSL license, but the BSL license just says that like you have to use it in the context of the testnet or mainnet, and if you do that, then like you can go and have fun. There's no weird limitations beyond that. We have a pretty phenomenal team that's been building this out, and it's now in 0.7 release, and there's going to be 0.8 and 0.9, and eventually get to 1.0, or we'll join the elite clan of 0 version applications. We'll see. And so to really understand kind of like the nature of how the database works on a super abridged level, because I want to spend a little more time this talk talking about authorization and all that fun stuff. But foundation, it's based around this idea of IPLD, immutable data structures, CIDs, preaching to the choir. So I'm not going to spend too long here. We have this like Merkleized DAG structure, which is a DAG that points to DAGs. It's a DAG of DAG, and its DAG is all the way down, and it's pretty great. Now, what we put in that DAG is really kind of the important part, and was the core insight in actually making the database work and function like a database. And this is going back to the problems that I was expressing before when we tried to build out against something, or like up against IPFS OG, vanilla original IPFS. And the problems around there was just that like it kind of was a file system, and like it kind of was a hypermedia transfer protocol, and like building against the ideas of immutable data for a developer coming from traditional domains is kind of an awkward data model, an awkward environment to develop in. And so we knew that we wanted all those same principles. We wanted immutability for the purposes of verifiable data. We wanted self-certifying structures. We wanted content linking. We wanted all these great stuff. And so we kind of built out the system based around delta state Merkle CRDTs. And shout out again to Protocol Labs. They were kind of some of the first to pioneer some of this work. And it's been just like phenomenal for so many different reasons. But basically, delta state Merkle CRDTs combine all of these like good parts, all the goods that I've been mentioning. It takes the ideas of CRDTs, which for like a quick abridged intro there, CRDTs stand for conflict-free replicated data types. They basically have this idea that you can have a set of data with some ideally common ancestor, and have individual actors independently make changes to that data, and always be able to come together and deterministically merge to some resulting state. We're using the deterministically merge to some resulting state is a very loaded statement, and what it means to merge to that state, and does that state represent the intention of what the users intended wanted to. It's a whole realm of very long and lengthy and complicated lattice diagrams and type theory and set theory and all that fun stuff. And there are many smart people working on this domain. But anyway, so CRDTs, they allow you to kind of have this ability to have individual peers on the internet be able to like operate on the same set without having to do like global and costly consensus is the rough idea. Now, embedding that into a Merkleized structure, it really allows us to do some interesting things. It gives us the powers of CRDTs by default, obviously, but it allows us to do that in the context of verifiable data, immutable data structures. It allows us to have like history and logs. It allows us to build out CRDTs without some of the common pitfalls, specifically around things like peer churn, and a lot of the traditional implementations of CRDTs. Any implementation of CRDTs need an idea of a clock. Clocks and time in distributed systems are unfortunately far more complicated than the idea might sound. And so the Merkle DAG kind of provides us that clock mechanic, which gives us casual ordering, which provides all the things we wanted to provide. And so this is really the absolute like bottom level, like layer 0 of the database is these delta state Merkle CRDTs. And then we've kind of wrapped a lot of this up in this fandangled query engine. I won't go into too much detail there. It's more of an engineering feat than what it is like a novel design feat to kind of make this all work. But what we ultimately get from this monstrous and beautiful query engine is this like very familiar, very usable, very functional and understandable database. And from the outside looking in, it just feels like a NoSQL database. It has the abilities, has like the guarantees of strong typing, has familiar developer experience around NoSQL document stores. It kind of operates over roughly JSON things, and it gives us the ability to have expressive queries over top of our data. And so we're able to kind of combine all these things such that we can just foundationally have this really nice database. But then you ask yourself, well, John, why'd you spend 5 years if all you wanted to do is just have this like Mongo style document store? And I mean, fair, that's a very valid question. But it turns out, from the outside looking in, you want this simplicity, you want these kind of like understandable and familiar processes. However, from the inside looking out, you have this much interesting, much more rich story to the data structures and how data works under the hood. And this is just an example. I'll go back just for a second. We have this kind of like system reserved query called latest commits. Really, this whole, actually, it's changed now since this particular slide was made. But this commit structure basically allows us to query our documents the same way that we would query our query a Git repo. And so it gives us that history, gives us that introspection and seeing how things changed, who changed what, all that fun stuff. And so from the inside looking out, the database has these mechanics of verifiable data and time traveling queries and peer-to-peer replication. I can and have many times spent a lot longer talking about the database in far more granular detail. But again, I wanted to reserve some of the talk today, or maybe the majority of the talk, depending on where we land, about the natures of authorization and how we kind of introduce the ideas of privacy and security, cryptographic primitives, and all that fun stuff into the database, ensuring authorization, ensuring people have access to the state users and all the things they need to. As an aside, one thing that isn't highlighted here that I think is really important is within the context of the types here, you have like a user type and your address type defined using GraphQL's wonderfully originally named schema language called the schema definition language. It allows us to have, define a type exactly as you expect. But the way that actually gets serialized into the state, and the reason why I explain that it's a DAG of DAGs of trees of DAGs all the way down, is that we actually have individual DAGs for individual fields and individual serialities to attach to those individual DAGs on fields, on documents, on collections. And the reason for that is that we can actually then have really granular authorization and access policies defined on individual fields. And it means that we can verify fields independently if you don't have access to a particular field because it's backed by a particular policy or authorization or whatever it is, then you can still have the full fidelity of using that document, just omitting that one particular field. And so having this like nested domain of DAGs of DAGs of DAGs allows us to do that really, really well. And as an extremely abridged view, I'm more than happy to pause for a moment to take some questions around like the nature of Defra. Again, it's far more complicated and far more powerful than I'm spending the 15 or 20 minutes talking about it today. But foundationally, we kind of have this really powerful, like natively feeling database that is designed from the bottom up to have the ideas that we talked about in the first couple of minutes, the ideas of interoperability and privacy and security. It has this ability to do like universal deployment. We have systems, or it's being worked out to be deployable to WebAssembly, to like IoT edge devices, directly to ARM chips. And so again, we want to have this idea that the database sits at the point of data generation. That's when you get into the system. That's when you make sure that you have this end-to-end guarantees around data locality, data history, data governance, all that fun stuff. And from there, you build out databases in this peer-to-peer replication model as opposed to this client-server replication model. And then you go out and you have fun and you party because you've built a cool database. But
awesome.
Yeah.
So this is this is super great. I mean, I think I definitely am seeing like all the other talks like branching off from here.
Yes.
And like I said in the chat, a slight hand wave over 5 years of work.
Yeah.
Aaron has a couple questions. He asked earlier why libp2p, and he's now saying, how do you do the structural hashing?
So why libp2p? That's a good one. I really like to phrase libp2p in a very specific way, which is that it is the worst peer-to-peer networking library, except for all the other ones.
Yep.
Because peer-to-peer networking is a pretty complicated and messy domain. You can ask any of the engineers on a team, and all the integration tests and the flakiness and all the complicatedness about, testing this database, all of it comes from, making sure the peer-to-peer replication, synchronization, and connectivity and all that stuff works the way it needs to. And so we're able to rely on libp pretty heavily to do a lot of that. There's still many instances where we have to kind of dive down and re-engineer a couple things and make it work to our liking. But yeah, so it's basically a necessary evil, and we're not going to spend the time on top of everything else to build out a brand new peer-to-peer networking library. And so it gets us more or less where we need to be. And the next question was structural hashing.
Yeah.
Is there like additional context?
So you mentioned that you want to verify one field inside of an object without necessarily having access to the other fields.
Yes.
If you would like to be able to verify, the third and seventh key in a map, but not any of the others, then you need a kind of hash tree that is structural and is not, I'm going to assemble the object, serialize it to bytes, and then hash that.
Yeah. So it basically boils down to the fact that we have individual Merkle clocks attached to the individual fields, and then we bundle up those Merkle clocks as opposed to bundling up the fields into a single IPLD object and then anchoring that IPLD object into a Merkle clock. It gets into some kind of like fun engineering, but there's, I'd say, nothing foundationally complicated from, like, for example, like homomorphic hashing. We don't do anything like that. It just gets us to a point where if state is, say, for example, encrypted, depending on obviously when you decide to encrypt that data and how it gets encrypted into the Merkle clocks, then we're able to basically ignore that Merkle clock that we don't have access to, take it on face value that the CIDs are what the CIDs are, and ultimately, because they're basically behind an authorization gate, we don't actually care what they are, other than the fact that they kind of allow us to get to the ultimate root CID, doing the things that it needs to. So I wouldn't say there's anything overly novel about that specific approach. Like I said, no homomorphic hashing or anything. It's just kind of this collection of Merkle clocks as opposed to everything get embedded inside of a single IPLD object.
You're pulling each field out into its own IPLD object.
Yeah.
Almost feels a little bit more like Datomic than a sort of Wikipedia over IPFS.
Yeah, I would say it's you could say it's close to that side of the spectrum. And I'll definitely, admit that there's one very like notable design decision that we've made, which is like we basically assume like storage is ultimately like free. We have pretty significant storage bloat because of the way that we structure the data in our serialization mechanics and having these like DAGs of DAGs of DAGs and all that fun stuff. So we basically assume that like storage is cheap now, it's going to get cheaper in the future. So it's going to be one of those trade-offs that we get to make.
Yada, 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 roll up proofs.
Exactly.
Storage may be close to free, but latency isn't. If you have something that's really doing blow up, you have to put those objects through a CPU to read them.
Well, so like ultimately, with you, when you have like IPLD objects, we have a series of ways to kind of like minimize that effort. We're working on like minimizing the amount of IPLD round trips using car files. And so, verifying hashes is a rather quick job because we're not doing any complicated hashing. And so basically just putting that storage, whether or not it's the histories of documents and changes and all that fun stuff, ideally is done away where it's relatively efficient. One thing I didn't get too much into, this query that we have here, obviously we're not returning back the more complicated query here. This is the more complicated like clocks and clocks and clocks and all that fun stuff. But when you're just using the database, you're designing, running filters, running queries, doing all the fun stuff, doing the things you expect a database to do. And so there's a whole suite of actually really interesting cryptography that we're doing that basically allows us to produce state proofs over top of the like computed filter set of your query. And so there's some like trust assumptions happening there. So it's not like the same level of full ultimate like granular verifiability. And this is because you want to do this, or you want to use these state proofs on systems where you might be resource constrained and you do have like less available, for example, compute. And so these state proofs allow us to do a pretty significant amount of work at the point of like the host, as opposed to the point of the receiver. And they'll attach these state proofs, and you're able to kind of have some degree of trust in the resulting set of data you get back from your query, compared to if you just wanted to like consume down the whole collection, run the entire like end-to-end verification of that DAG and bags of DAGs, and then run the query locally. Cool. All right. I will move on to authorization, and how we kind of like protect all this lovely data that we've been hashing and combining and computing and structuring. And so that's where Zanzi comes into play. And Zanzi is our implementation of a infamous paper that came out of Google called Zanzibar. And I have no idea why it's named Zanzibar. There's this idea that it was once called SpiceDB, and that someone along the lines at Google changed it to Zanzibar because like the Zanzibar Islands are casually referred to as the Spice Islands. Anyways, there's not really much lore behind it. Even worse, there's no cute like logo graphic that we can point to and say like, hey, that's Zanzibar. So I don't know who your designer is over at Fission, but like you should tell them to whip something up, because as you'll see in this talk in a couple of minutes, I I struggle to come up with a nice logo to represent the general idea of Zanzibar. And love, we kind of have this notion that if it doesn't come from the Zanzibar region of Tanzania, it's just sparkling authorization, and that was definitely said by some Google engineer somewhere in the world. So, what is Zanzibar? The paper is called Google's Consistent Global Authorization System. It is like very paramount and very definitively on the authorization service ACL side of the spectrum when it comes to ACLs versus object capabilities. It defines relations using this, defines authorizations as these forms of relationship-based access control, as opposed to role-based and attribute-based access control. And it does that by basically storing and describing the nature of relationships over graph-based RDF tuples. Because Google is Google, they built it on Spanner. Now, usually that would just kind of be an implementation detail, but there's actually a lot of really cool things built around Spanner that allows you to do a lot of global authorization and global consistency for like relative free. So they don't really have to think about too much. They basically have atomic clocks at all of Google's data centers, and so things work a lot differently when you have atomic clocks to work with, as opposed to like this hand wavy notion of Merkle clocks or vector dot clocks. And so when you have the literal power of the atom powering your data structures, you can do some interesting stuff. And then it acts as just a general purpose global authorization API. It is actually interesting that they released this paper, because the system that this is describing does actually power a significant amount of Google services. And so obviously we can understand and appreciate the scale of that kind of deployment. On the right here, you can see, it is just this relatively straightforward tuple definition of, the tuple set of object, relation, and user, and you express that over a graph, and it turns out you can actually do some pretty cool, fun things over those graphs. And there's my little logo that I have attached to Zanzibar. So if you guys can do something better, then by all means, open invitation. And there are a bunch of other open source implementations. All of them are based around this idea of like, cloud native SaaS, all that fun stuff. They're all really good. Some cool engineering that's happened in all of them, and there's more than I've listed here. But there's a bunch of different reasons, and we'll get into that, why we need to kind of build out a slightly alternative implementation. And so, when you have your data, your authorization system built around this notion of graph tuple stores, which again, tuples are the the set of subject, predicate, object, or relation, depending on your chosen word there. It turns out you can kind of construct these really powerful and really broad authorization systems, for lack of a better word, and it allows you kind of build this really really well designed, really like hierarchical system to your authorization, where you can have, you know, this implicit and explicit set of relationships, and you can kind of like compose your authorization state into this like really rich domain, and it allows you to express then policies and access rights and permissions over that graph as like a set of graph queries defining that there is like paths between X, Y, and Z. It does get kind of like annoyingly complicated from an implementation and engineering standpoint. And I don't know if Bruno's on this call, but he can certainly attest to that. He's our engineer that's been primary in doing a lot of this stuff. And so, you know, there's a lot of details that the Zanzibar paper glosses over in terms of implementation and how to actually make this like performant, which is its own bit of nightmare. But foundationally, like this is the data model. And it allows us to do things like expressing the fact that Bob is a guest on the Anvil repository, which is owned by the Acme organization, to which Alice is an admin to. And when you have that relationship, as again, you can express these permissions, these computed permissions on top of these relation graphs, these tuple store graphs, to be able to express really, really interesting, really powerful mechanics. The API is like exceedingly simple. There's like some tangential stuff that is like outside the core of it, but basically it comes down to the fact that like you can write a tuple, which has the three sets, the three values. You can check if a permission over like a tuple exists, of which that can be explicit or explicit, indirect or direct. And then you can run this like expand call, which is basically just kind of a reverse lookup over just a user set, which is a relation object. And so you get back the user sets, all the user sets that match that relation object. User set is basically just a computed set of subject actors in the graph. And it operates as a consistent and partition tolerant system as far as cap theorem is concerned. So I'll let you all take a moment to guess where you might think that Zanzibar lands on this, the spectrum. And once everyone's locked in their answers in their mind, obviously it's like by definition a centralized system. That's fine. Everything that Google does is centralized, so like they couldn't care two poops about how to actually make this work in something like a decentralized setting. And so the Zanzibar design, the implementation, all the fun stuff is based around this notion that like there's a trust authority, and the trust authority gets to do whatever the heck they get to do. And if you don't like it, then you can go, I don't know, use Mozilla ? However, it turns out we do want this notion of kind of a decentralized authorization, because we don't want to have this, you know, all this beautiful engineering goes towards our trust protocols and our decentralized database and our peer-to-peer schema management system, and then like, oh, just plop a centralized authorization service in the way. And so Zanzi is our implementation of Zanzibar for the decentralized setting. And the first kind of way that we make that work is we use a Merkleized IAVL plus tree to kind of act as the core, what we refer to as the committed state. And it's important to kind of recognize the committed state versus what we'll get into later, which is the uncommitted state. It is, you know, going to do exactly what it's going to do. That's a very horrible phrasing to say that like a Merkleized tree gives us like membership proofs over the state that's in the tree, or the store, I should say. And so there's like two implementations technically of Zanzi. There's like the core engine, which is designed to run inside our application specific blockchain or sub. And so there are technically two implementations. We don't have a very good terminology internally to how to like distinguish the two. So I'll just refer to Zanzi as the general decentralized implementation, despite the fact that there is a core engine that gets embedded and executed inside a like decentralized Merkleized system. In addition to the Merkleized IVL Plus store, which contains the committed verifiable state, we have a second store that allows us to actually run these graph queries in the context of a blockchain in a much more fast and performant way. That is called RaccoonDB. And apparently all we do here at Source is just build DBs. There's like 2 others I haven't even talked about. So I used to, tangentially, I used to say to anyone that would listen, that if you found yourself building a database, you have like done something foundationally wrong in your life, you need to stop, turn around, reassess, and figure out what went wrong. And so I objectively can no longer say that, but I get to make a joke about how I used to say that. So, it's a win-win. And so RaccoonDB is basically a secondary index, a graph-based secondary index that operates on top of the Merkleized IVL tree that is uncommitted, that doesn't have a verifiable state. That's okay because the execution of the graph algorithm itself doesn't inherently need to be verifiable because the resulting tuples that like match the path from A to B are in the committed state and are verifiable. And so it allows us to kind of do this system in a way that's performant. It runs on chain, and we're able to kind of leverage a lot of the fact that like a lot of it exists on chain, some of it exists off chain, and we're able to produce these kind of like cryptographic guarantees that things are running the way they're supposed to. So I'm just going to take a quick sip of water while everyone watches and ponders and appreciates this beautiful artistic diagram.
It is. This is great. It's an awesome walkthrough. And question. So runs on chain for completeness. You use the Cosmos SDK, and then Raccoon runs
inside the chain
on your nodes.
No, so Raccoon is like an alternative store that runs on chain. And so we do these graph algorithms from the perspective of the validators, but because it's not a write, it's a read. We don't have to do any complicated like transactions and global consistency because the committed state is the written, verifiable, transacted, authorized, signed, all that fun stuff state. And then Raccoon basically just runs in the context of any node that happens to be in the blockchain. Obviously, validators, full nodes, sentry nodes, all that fun stuff, archival nodes. And so RaccoonDB basically works as almost like an index. I mean, not almost, like it is an index over top of that data and doesn't require coordination between the nodes to execute.
Great. Awesome. Thank you.
Thank you. And so Zanzi operates as a Byzantine fault tolerant, or over top of a Byzantine fault tolerant consensus engine. As Boris said, it runs using the Cosmos SDK, which itself is built on Comet BFT consensus, previously named Tendermint consensus. And there is a whole dance to making like the BFT stuff work. But the beautiful thing, and one of the very important core decisions about like kind of splitting out the state between the like committed tuple store and then the graph state, or like the graph relation state, allows us to commit the important data to state and pay that cost of writing tuples and sending transactions and doing all that fun stuff through this complicated polka dance diagram. And then once you have this committed set, you're able to run these more efficient graph queries on top of it. And so it is like by definition like no secret by any means that sending a billion writes that Google needs to do every second to a blockchain is like not going to be performant, and it's not going to scale to the same degree that like something built on top of Google Spanner would. However, because of the way we've designed it, we basically at the moment have we don't have the ability to do like cross policy like queries. Like we do, but like specifically for the purposes of performance, we're limiting it because one of the things we can do is basically like very easily and arbitrarily shard the system. And there's a lot of cool mechanics and inventions over in the Cosmos world, to which if anyone hasn't spent time looking at, I highly recommend, because it's pretty powerful and fun set of technologies and stack and ecosystem. And so using something called ICS, interchain security, we basically like arbitrarily shard the system over like individual policies really, really easily. And so, we're able to get to a pretty high degree of scaling and then global quote unquote authorization using the system, despite the fact that it does pay a hefty tax of using BFT consensus.
So when you say policy, there's lots of hand waving here, but
yes.
Essentially you will end up having a certain domain app query that you can scale independently, basically.
Yeah, and so actually, I should have added an example of what our policy DSL looks like. But basically, you define resources. In those resources, you define relations, and in those relations, you define computed permissions. And so, usually for the purposes of our like, I should say that everything at Source is designed to ultimately work together and harmonize together, but nothing is explicitly dependent on one another. It's all relatively plug and play, nice abstractions doing what engineers do. And so, although this does work as like a general purpose engine, there are like design decisions that have made it so that we do try to tailor it towards the needs and requirements of DEFRA. And so with that, when we define policies in DEFRA, we define it on like a type level, and then we can annotate individual fields with permissions based off of that policy. And so a policy is like a self-contained unit. You can kind of think of it similar to writing and deploying a smart contract into, say, something like Ethereum, where for the most part, like, you have your state and your functions and your views and your queries all defined and all encapsulated in that smart contract, in our case the policy, and that gets like submitted and anchored on chain. And so at the moment, when you define all those things, then insert tuples into the context of that policy and do all the things you need to, you're basically bound to the state inside the policy, or like the expressed resources inside that policy. And so this is what allows us to do that, like this high scalability sharding stuff that we're working on, because it's all nice little prepackaged policies that say like, this is a type where, like, let's see. Types like resources being things like users and organizations and repositories and issues. This is obviously an example coming from like a GitHub style implementation. Users is a interesting one because it's a predefined type. It's basically a did type, of which we use dids everywhere throughout the system, for reasons I don't think I need to describe to this particular crowd. But dids are awesome, and they're able to do pretty cool amount of things. And so dids are kind of like baked in as like these user actors. And then when you're defining resources, they're defined as like organization is a resource, repository is a resource, issue is a resource. You're able to define relations among these resources, these like parents and admins and guests and owners. And you can define that however you wish across however many resources defined over that policy. And then you define these like computed permissions that say like, you can read if you're a parent, owner, admin, or you're a guest, or you're a member of the collaborator set, like, or. And so we have a express in language to do like relatively straightforward set operations across any set of relations. And so that's roughly, again, I should probably have an example policy in this.
Yeah, no, that's good. I think painting in some pictures here of what this looks like, it's really good. Let's keep going because we got a bunch to get through.
Yeah, that's fine. We're almost there. And so there's only two changes that we ultimately make to the Zanzibar API. We have a check call that returns back a proof, and I'll gloss really quickly over what that proof is, but I will get into like how it works and why it works. And then we have a verify call. The verify call, it can be run locally. Doesn't have to be run in the context of any chain. Like anyone, anywhere in the world can run this verify call, given that they have a proof and the like tuple that they want to go against. And so, obviously, I get to spend a lot of time talking about this proof. You can see this left-hand mechanics here. I will do an extremely abridged introduction of Verkle trees, like extremely abridged. And there are many resources on the internet to find out more. At the basic idea, a Verkle tree is a Merkle tree, but instead of using a like hashing function like a SHA-256, we use a vector commitment. And the reason why we do that is that if we expand the like children's of a Merkle tree, we have like a much wider and a much shallower tree, but we don't save anything on proofs, because with Merkle trees, you need all the sibling adjacent children's at every level. And so you don't save space if you have, for example, a 16 array or a 256 array Merkle tree. However, that is not the case for a Verkle tree. It is not unheard of, and actually there is a design decision on Ethereum to make this work, where you have 256 children per node, going all the way up to a 1024 children per node. And the reason why we do that is that when we generate proofs on a Verkle tree, we do not need the sibling values. You only need one per level. And so you optimize your tree to be very, very stumpy, to not have a lot of height. And so to do that, we expand the width. And so Verkle trees are like this beautiful, magical thing. I have the saying that like, if you ever have a problem in like cryptography, just like throw a vector commitment at it and it magically goes away. And that's like pretty foundationally true in this Verkle tree implementation. And so when we basically run this check call, we store the path, the traversal path, more or less, from the raccoon state at some future point in time if you need. And we'll basically go and like submit this and store this into the Verkle tree state, and we can get back these like proofs. And the really cool thing about Verkle trees, which if this alone didn't like blow your mind, you might have to strap in for a second, is that you can create proofs of an unlimited number of values, and it doesn't grow in size. The proof does not grow in size regardless of the number of values. Obviously, like you need the set of values to like prove against, and that will grow linearly, which there's nothing you can do about that. But you can prove 100,000 million, doesn't matter, entries or leaves into this Verkle tree, and you still have the exact same single 32 byte proof, plus or minus some like metadata, which is like, honestly, like I went to school for cryptography and number theory, and like the amount of math that goes towards making this work is like crazy. And so Verkle trees allow us to do a lot of the mechanics here around this authorization. Now, for the last, how long are we supposed to do this? 1:15? Unless we're supposed to be done at 1. I think it's an hour and 15, right, Boris?
No worries. We've got you here, and people are listening, so people may need to drop off, but let's keep going.
Beautiful. And so, what does all this have to do with like UCANs and all this other fun stuff? And so it turns out that we've kind of like devised this way that this can fit really nicely with UCANs, despite the fact that on the face value, this is an authorization service. This is like a global authorization service and fits closer to the ACL side of things than the object capability side of things, to which obviously UCAN is. And so, we've kind of been exploring down this domain of getting UCANs to work in Zanzibar, and we've arrived at something interesting, and so it's good to kind of like tell you all about it. So obviously, this is a domain that we operate in for Zanzibar. It is, and huge shout out to to Brooklyn for these wonderful slides from one of many slides that she's done over many different presentations. So I will shamelessly steal them and use those to describe the nature of UCANs. Obviously, we're a ACL service auth, and this is the problem domain that we're in. We have this magical actor that sits in the way between you and resources, and they basically dictate if you do and do not have control or access to a particular resource. Now, we get around some of the issues around ACLs because we have this decentralized mechanic. There isn't a single trusted actor. We can't have the bad admin problem, all that fun. But the other side of it is, because we have these proofs, these Verkle tree proofs that are succinct and awesome and magical and beautiful, we're able to do some pretty cool things that kind of shifts our whole system closer to like somewhere in the fuzzy middle between ACLs and object capabilities, because you can take these proofs and you can start doing some fun stuff with them. And so on the other side of the spectrum, obviously with UCANs, operating as a capability model, you have the tickets. Anyone that has the ticket for the object capability can do whatever it is that object capability says that they can do. And the key importance and value, at least that I see with UCANs, is this ability of kind of having these delegation capability chains, where you can kind of attenuate and potentially amplify capabilities using this like verifiable chain, to which there are proofs and all that fun stuff. And so this is the domain, obviously, that UCAN exists in, and this is the domain that we exist in fuzzily, sortily. The problem that we've experienced with object capabilities, and I've experienced in the past with a myriad of different systems, has to do kind of twofold. One, with object capabilities, you kind of have this like revocation problem. Obviously, you can't globally revocate an object capability. It exists in the world, and anyone that has it has it. You can kind of do these weird bastardized workarounds, but like it is what it is. But the trade-offs you get are pretty significant, pretty important. And so, a solution to revocation is having short, basically expiration times on the object capabilities you get. And so, if I am Joe and I have my resource on nft.storage, and I want to give Alice, access to that resource, I'll make an object capability UCAN token that says like they can do that, delegate, all that fun stuff. But when it comes to short revocation times, we kind of have this problem where there's like this interactivity problem, issue of just like constantly needing to go back and forth and like interact with the original owner, get these constantly get refresh tokens, like so on and so forth. And like if what happens to the token, the person that owns a resource like goes away or dies or like something, who knows. And so the sequence diagrams around like constantly having this interactivity problem is like can be pretty paramount depending on the way you're using them, the nature, all that fun stuff. And so there's nothing inherently wrong with object capabilities and revocation models, but this is kind of a side effect, consequence. But it turns out, and one of the kind of important details, and like one of the reasons why we like made Zanzibar or Zanzi as a whole, is that we can kind of do some interesting stuff with them. And so we have this like code name skunkworks project going on called Zazu, of which Zazu is the name of the bird from Lion King, to which is a toucan. So I thought that was like, actually, I don't technically think it's a toucan, but he looks like a toucan. So the lore stands.
Lore, yes, the exactly. Lore stack.
Exactly, that's the important part. And so Zazu is Zanzibar authorization with UCANs. And so because we kind of have this like proof thing that we are able to mint from our implementation of Zanzi from Chain that has like succinct and verifiableness and all that fun stuff, we can kind of take the idea, from actually really the original macaroons paper, again, out of Google, where they kind of talk about this idea of this like a golden macaroon that gets minted from services. And so now we can kind of take this instance of a UCAN and have it be minted, like have the original, the root level UCAN basically be minted directly from the Zanzi implementation, to which the proof contains the token that came from the Verkle tree. And now you basically just have like an object capability, more or less. You can take the rights that are defined over that proof and stick it effectively into a UCAN, of which the troubles and design decisions that we have to come up with is basically trying to find alternative ways and define alternative ways to define different proof mechanics in UCAN, to which at the moment there's like a default assumed proof mechanic. And so, for example, things like from the JSON or not from the DID world, they do specify alternative ways to like verify, or like the quote unquote verification method is kind of like in line with how the DIDs are communicated. And so we're kind of like exploring ways to make that work in a interesting way. And so obviously talking to you lovely folks is an important step in making that work. But the general hand wavy idea is that like you basically mint this golden macaroon, this golden ticket from Zanzibar directly, that is attenuated for a particular set of permissions for a particular person. And from there, it's just UCANs all the way down. And so it kind of has this like benefit where you can do a lot when you have the service minting these tokens as opposed to the individual resource owner making those minting those particular tokens. You reduce the interactivity problem. You can do things around global verification, but that's a design decision that you basically have to make up front one way or another. But once you get past this first step here, this first cloud Zanzi step, and into the root step, again, it's just object or UCANs all the way down. And that's something that we've had a really good time with because, in general, we're a huge fan of object capabilities because it allows far more powerful like local attenuation and delegation than service auth. And it doesn't require going to the chain and updating state and like anything like that. And so if you can do like your basically minified set of authorization state on chain, mint these like golden macaroons, these golden Zazu macaroons, and then stick that in UCAN, then like we basically kind of get like a win-win-win because everyone's great and everyone wins. The infamous triple win.
There's a triangle in here somewhere. Exactly. And I like the centralization to decentralization.
Yeah.
And there's this other piece where UCAN is right at the edge, but you've got to, and it's the third piece of this triangle. And Brooke, I'm sure she's like, oh yes, this is a well-known triangle. Go ahead.
I'm glad that it immediately piqued Brooklyn's interest.
Yeah. So my totally makes sense, right? It as I put in the chat, reminds me a lot of how Ceramic does things, where they sort of like anchor things on chain.
So I should quickly apologize. I haven't been paying any attention to chat, so hopefully I haven't missed too much there.
No, everything that's needed to come up has been brought up as we go, so totally fine. Yeah, so Ceramic does something similar, right? Where they get concurrency, sort of, with certificates, and then they anchor it on chain.
Yep.
The thing where object capabilities can't be revoked globally, actually, like they can be, right? And then since you're already rooting everything in a chain as the single place, is the idea that these will get then rolled up onto the chain and basically anchored there, and then any verifications also go back into the chain, basically, more or less.
These being
these UCANs. These macro-like things.
Yeah, so the idea that if you revoke that like top level one, then ideally it should revoke the rest based off of the delegation property. And so you actually, as far as like we've been exploring, you don't have to then go and further like attenuate and root these like UCANs on chains, which I don't believe they need to be like rolled up and anchored into the state and the committed state. But like I know there's, again, like the object capability model and like revocation, there's kind of a long history there. And so there are like obviously a myriad of ways to do that. One such is like going directly to like the service and saying like, this is the UCAN that I've minted and I don't want it to exist anymore. The global verification becomes a problem where like if you have a myriad of different services that are potentially bound to like a UCAN. And so anyways, it is just like a generally interesting domain problem of trying to do this like by globally I mean like globally across services, across things, like all roughly within like a single call. And so you absolutely could do that, and like if you have just like a dedicated again, I use the word trust protocol pretty broadly, blockchains, it doesn't matter what. And so this is good. Again, our just alternative to being able to like leverage UCANs in the Zanzi model that allows us to kind of do the things they wanted to do. So
yeah. Like I get that it gets you out of having to always go back on chain. It's almost like a side chain that you create, right? Yeah.
This is local only side chain, yeah.
But so you can only revoke the initial golden token, golden ticket. Are you able to then revoke anything that's like further down the chain, or do you have to then revoke that entire UCAN lineage?
So any revoking down the chain would have to basically just follow the same revocation model that UCAN's been exploring already, to which I have kind of gone down the revocation draft that was posted there. And so yeah, so this is my point. Like after you get from the Zanzi model into the like root witness invoke model, then like it's just UCANs and you get to do anything that UCANs get to do. And so at least for us at the moment, you don't have to add the additional revocations on chain, because the only one that you can revoke, on chain is the minted one, the golden macaroon.
Yeah, makes sense. I wonder if there's actually, and without obviously I'm
hijacking.
Yeah. So maybe we should take this offline after. I actually wonder if there's some Verkle stuff that actually might be really interesting in here where you'd be able to get both, but we can keep that after. Anyway,
exactly.
That was my main question, was about the anchoring. So.
Yeah, we're like I said, we're definitely relying pretty heavily on the Verkle mechanics here, to basically act as this mechanic. And so, but like I said, like the problem for us was kind of that twofold. One of the reasons why we have Orbis, the decentralized sequence management, is that, again, when it comes to PKI and interactivity, you don't want to always have to be going back and forth and like knowing who your keys that you need to share with, and like going through that process of peer-to-peer interactivity, especially if that peer is offline or they're gone or disconnected, or the internet to the nation that no longer exists, like all these things, right? And so, yeah, it's that kind of double-edged sword of interactivity and revocation. All right, that's cool. Anyway, so that's all I have. And it allows us to, in summation, we do have this like pretty powerful stack around interoperability, privacy, and security, where you kind of have this user as like the focal point, databases deployed into user devices, databases communicating and facilitating data between user devices, between services, ideally universally using various deployment methods. You have all these abilities to do this local first development and application state. You're able to have this like agency and consent and all this powered by Merkle securities. You have the ability to like encrypt things end to end without having to coordinate with PKI through Orbis. You're able to evolve and mutate and change your schemas using Lens VM with this bidirectional schema system, and bake all that together with this on-chain, off-chain pseudo authorization system, which ideally gets connected into UCANs. So that's what we've been working on.
Amazing. Awesome. Thank you so much. That's great. I mean, and we all know, I kind of put up the bat signal and said, hey, anyone interested in this space, let's come and get a source network overview, which you've done. Like, again, like each one of those are definitely a full talk.
Exactly.
I'm so pleased that we've got an initial video and a background for folks. What do you want from people right now? What piece of this do you want them to try out? Where's the so there's the everything part of other people building protocols or platforms or whatever. But where do you get started? What's the we've kind of got the like odd SDK for front end developers.
Exactly.
Is Defra the starting point?
Yeah. And so for us, really any one of them could have been the starting point, but for very many reasons, Defra is kind of that like jumping off point. And then you slowly can kind of start introducing the other bits and pieces when like the development dictates it, when the application dictates it. For example, one of the things here is that like Defra can kind of act as a nice Trojan horse to, get traditional, non quote unquote decentralized projects to kind of like start incorporating more and more decentralization. And so in general, for us, like go to the Defra GitHub and just like poke around, see if there's more that piques your interest there, like take it for a spin, and just like reach out if there's mechanics that are interesting to you, if there's use cases that are kind of matching these primitives and these design decisions, and we're happy to talk more about it. But for us, it's really just about like getting it in front of the eyes and ears and hands of developers, and kind of just seeing where those conversations go at the moment.
Amazing. Yeah, I mean, I think we've got lots and lots of people coalescing on UCAN as a certain layer, but it is like more like a protocol layer. I was just having a call this morning with the Shovel company, who are a team in India, and they're like, okay, but what about accounts? So I think that's a whole other discussion that I'd like to have at some point, is how all of us who are working on UCAN can be interoperable through that layer. But the next one for both developers and end users will end up being like, great, what's a layer there? And we've heard some Blue Sky has UCAN on their roadmap, and as far as a user base goes, they're the single largest end user base.
Exactly.
They're somewhere around 1.5 million users that will have UCANs as part of their system. which is great. And they have like a recognizable name. And it's a bit of a replay of some of the pattern of like the early Web 2.0, early OAuth, login with Twitter, login with GitHub. And I think we have to, that's a layer that we have to show some interop on. So I think that's some next step for us all to dig into.
Yeah, no, it's absolutely perfect. And one of the things we really tried to promote is the fact that like, ultimately end users don't care that we've like built this on Cosmos SDK. They don't care that some do care that it's peer-to-peer, but like they don't care that it's necessarily peer-to-peer. Like, but we actually start listening out like what are the gains you get out of this? Like that's the part that we all collectively need to be focusing on. And I think the fact that Blue Sky being an example here, they're able to promote this idea, even though that like there are issues around peer-to-peer and centralization there, but like it's enough to the point where like it's there that like users can feel comfortable about it. Like users have the ability to have like agency and consent. And so with having UCANs as kind of this like shared primitive amongst a lot of services, a lot of projects, a lot of like applications for users, that alone is kind of like a huge step towards the ability to have like generally hand wavy interoperability of application and data. If you can at least have this notion that we can all agree roughly on how to express whether or not you even have access to that data, which is a pretty important first step. And so definitely a huge fan of the UCAN model and trying to find ways more and more to integrate it. Bricklin.
Go.
So two other questions, just because I wasn't, and I might just be like clicking on the wrong things. So you had mentioned the ZKKMS and I can't remember the name of it in your system, but it's essentially Cambria.
LensVM.
LensVM. Where would I find more out about those two things?
So the ZKKMS is not generally publicly available at the moment, but I'm happy to kind of like have a separate call and kind of play around with that, or I can just send you some additional follow-up. However, LensVM exists on its own org, its own GitHub org, and I can post the link in chat. And so with Lens being like generally useful for a lot of different domains, even beyond what we do, we did want to specifically kind of like isolate it or separate it out into its own thing for.
God, the more GitHub forces 5 years ago,
the more GitHub organizations you have, the better is clearly the rule, right? And so a huge shout out like the original Cambria stuff and a lot of the follow-up talks I've had with Ink and Switch and the people over at the local first Discord group, and it's just been a big win over there.
Awesome. We should we're coming up on an hour 20. Thank you so much, Sean. This is super awesome. Really great start, like I said, of the overview of this, and looking forward to mascots and interop. I'm not sure which comes first, but there's a lemma in there. Well, maybe I can make Boris's triangle design, right? Where one of them creates logo mascot.
First development. Yeah.
Thank you again so much. I am going to stop the recording. And
thank you.
That button.